Hello guys, welcome to Physics Grad. In this video, we are going to study about principle of least action. Before you see this video, you have to go through one of my videos in the maths playlist, which is titled Euler-Lagrange equation, because this will be a prerequisite to understand what I'm going to explain in this video. So, having said that, let us begin. So before I start with what is principle of least action, I want to say that this concept is or falls under the regime of what I would like to say abstract maths. So it's hard to relate it to our daily life and what we see around us. And that is why instead of simply starting off with some equations, I would like to start with a simple analogy. And that is how I would like to begin. So I'm going to formulate or start with the following scenario. So consider a terrain which is like a hill. Let's say something like this. Now, let's say that I am going to put a small ball at some initial position. So by the way, this is defined in the XYZ coordinate. So X, Y and Z. And so in this terrain, if I initially keep a ball at this particular point, how is this ball going to roll down? So how does the ball roll down? Now, before we answer this question, I want to make this particular problem a little bit less complicated, and the way we are going to do that is by the following assumption. So the assumption is that the speed of the ball is infinitesimally small. So what this means is that as the ball rolls down, after it covers a small distance L, so after it covers a small distance dl, the ball is stopped by some external force. Okay, so what this means is that as the ball travels a distance dl, I'm going to stop the ball, making its speed 0. And once again it may travel some dl, and again I'm going to stop the ball. And as dl tends to 0, whatever the velocity it gains as it goes from this point to this point is going to be very small, and since I'm stopping the ball, its average speed will be infinitesimally small. So this is our assumption. So what this assumption implies is that kinetic energy can be neglected. So kinetic energy can be neglected. So the assumption again is that there is some external force which makes sure or which ensures that the velocity of the ball or the average speed of the ball or the speed of the ball is going to be infinitesimally small. Okay, so with this, how does the ball roll down? Or of course it is rolling down very slowly, but it is going to follow a particular path as it rolls down the hill. Okay, so let us say that that particular path is something like this. So it can take many different paths. For example, it can take a path like this, or it can take a path like this, or it can take a path something like this. But what is observed is that it takes a particular unique path which is dependent on the initial position of the ball. So why does the ball take a particular path? Why not take any random path? So to answer this question, we need to know what is the condition that is followed when the ball follows this particular path which is shown in white. So the question is that how does the ball decide the direction in which it has to go? So how does the ball decide the direction in which it must go? So what determines this particular white path? What is special about it? That is the question we are trying to answer. So for this, let us consider that as the ball rolls down, it has come to a particular position. Let's call this position R. Now at this position, from this position, it can go in various different directions, which I'm going to denote it this way. But the ball is going to choose one direction. So ball chooses one direction, but based on what? So in this particular case, as what our intuition says and from our knowledge of, let's say, 11th and 12th standard physics, the ball chooses the direction in such a way that the decrease in the potential energy is maximum. So in this case, it chooses the direction where there is highest decrease in potential energy. So in this case, it chooses the direction in which there is highest decrease in potential energy. There is highest decrease in potential energy. Of course, we are talking about gravitational potential energy here. Okay. So this is based on the assumption that any system tends to go towards the state with minimum potential energy. So what this translates to here is that the ball is going to choose a particular direction wherein change in the potential energy or the decrease in the potential energy is going to be maximum. So that is how it chooses this direction. So that is the condition that the ball must follow to choose the direction. Okay. So to be more mathematically precise, this direction at every point R is given by the direction of gradient of the potential energy function on, so this is on the surface of the terrain. It's defined on the surface of the terrain. So this particular quantity, gradient of the potential energy function, is going to give us the direction of maximum decrease in the function or maximum decrease in the value of the potential. So the direction at every point R which the ball is going to choose is given by the direction of gradient of the potential function. So this is a more mathematically precise statement. Now, we know that the ball is going to choose a particular path, but how do we exactly define a path? So how do we define the path? So I am going to call this path, I am going to put it in double quotes, is roughly sum of infinitesimal traversals. So what I mean by this is the following. So let us consider two different paths. Let's say path 1 and path 2. So what I mean by these infinitesimal traversals is that, let's say initially the ball is at a position denoted by the node A, and let's say that it chooses a particular direction and travels a length dl to the next node denoted by B, and from here again it chooses a particular direction and let's say it travels to another node C given by whose length between the two nodes is given by dl, and once again it travels to some other node D again whose separation is dl. So what I mean by these infinitesimal traversals is basically these guys here. So traversal is basically how the ball goes from one node to another, and here the node represents the position of the ball in the terrain. Okay. So that is how I am going to define the path. So path is basically sum of these infinitesimal traversals. So similarly, let's say we define another path from A dash to B dash to C dash and to D dash, and again each of these traversal are of the length dl. So good, now we have a sense of how to define the path, but how do we differentiate between them? So what is the difference? So what's the difference? between path 1 and path 2. How do we know that this path is different from this? Or how do we choose which path is in a sense better? So how do we choose a better path? So we need to somehow be able to differentiate between these two paths. Or in some sense, we need to say that one of these paths is more preferable by the ball as compared to the other. So how do we say that? The simplest way to do this or to formulate this would be to assign some kind of weights to each of these traversals. So I'm going to assign a weight W1, W2 and W3. Again here W1 dash, W2 dash, W3 dash for each of the traversals. So what have I done? I am assigning a weight. So again I'm going to put this in double quotes for each possible traversals. Okay, and I'm going to define something known as the cost of a path P. So in this case, let us consider P1. I'm going to define this as the weighted sum of the traversals. So in this particular case, this is nothing but W1 dl plus W2 dl plus W3 dl. So this is basically the traversal from A to B, B to C, C to D. And each of these traversals are carrying weights W1, W2 and W3. And this sum, the weighted sum, I am going to call it as the cost. So similarly, cost of path P2 is given by W1 dash dl plus W2 dash dl plus W3 dash dl. Now we have a way of saying which path is more preferable by the ball. Okay. So before we do that, how do we assign the weights Wi or Wi dash? How do we assign this? And the answer to this is simple. We assign it using this particular condition, that at every point R, it chooses a direction which has the maximum decrease in the potential energy. So this means that if we are at some node R, there are many different traversals possible. Okay. Now I am going to assign them with different weights. Let's say like this. And I am going to say that the weight is minimum for the traversal corresponding to maximum decrease in potential energy. because this is how the ball decides in which direction it needs to go. Okay, so let's continue. So we know that there is only one correct path. So there is only one correct path. So what is this path? This path is the one where the ball starts with the initial position and it traverses in the direction which it most prefers, which is basically in the same direction as the gradient of the potential function. So let's say it travels this way, and then again the ball stops because we are going to neglect the kinetic energy and we are assuming that the velocity is infinitesimally small, and again it decides the direction based on the maximum decrease in potential energy, and let's say it goes like this, and again like this, again like this. So this is the unique path which the ball is going to travel, which is going to satisfy our condition that the ball decides to go in a direction of maximum decrease in potential energy. So for this one unique path, some special condition must be satisfied, or what can I say? There must be something special, so which implies there is something special about this correct path. And what is this? What is the special thing about this correct path? And my claim is that this is the path with minimum cost. And by cost, I mean the weighted sum. Weighted sum of traversals. Okay, and this intuitively makes sense because for this quote unquote correct path, it always chooses the minimum possible weights for each traversal, and thereby it should logically have the minimum cost. So therefore we can conclude that the path corresponding to the minimum cost must be the correct path. Okay, so that is our inference. Now let's take the limit dl tends to 0. What happens then? When we do this, the weighted sum will basically become a weighted integral, and this implies cost of some path p will be given by the integral from some position r1 to r2 with some function called the weight function, which I would like to call the weight function, which depends on some quantities k1, k2 dot dot dot. I'm going to say what this k1, k2 dot 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 are, times dl. Okay. So when dl tends to 0, the sum has basically become an integral or has been converted to an integral, and the total cost for a given path p is nothing but this definite integral from some initial position r1 to some final position r2 with of some weight function over the path p, which is given by a series of traversals of length dl. Good. Now, before we go into what these k1, k2 dot 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 are, I want you to take note that w of k1, k2 dot 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 can itself be thought of as a surface in the space defined by k1, k2 dot dot dot. So what I'm trying to say is that in some space which is dependent on k1, k2 and so on, I can basically denote this function by some surface. Okay, and this particular integral is basically from some point to some other point, and it follows a particular path in this surface. So what I mean by this is that as the particle goes through these small traversals dl in the original terrain, for each of, as it changes its position, its weight is also going to change. Okay, so we can think of this k1, k2, that is the quantities which define the function w, or w will be dependent on these quantities k1, k2, which are somehow related to the position in the terrain, the directions or the different possible directions in which the ball can go. So possible directions at a given position, and it may also depend on how the potential energy changes along these directions and so on. So these k1, k2 dot 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 are somehow related to these things, because that is how we assign the weights. So at a given position, the weight will be minimum in the direction of PE, where the change in PE is going to be, or there is maximum decrease in the potential function. So now in the space defined by these quantities k1, k2, we can in turn draw the surface which denotes this weight function. And as we traverse a particular path, we are basically in turn traversing through some particular sets of k1, k2 dot dot dot, which in turn corresponds to a particular path in this surface. And this particular integral basically denotes this total length. And our condition of minimizing the cost basically boils down to going from this point to this point in a path which corresponds to the shortest length. So over here, minimization of cost corresponds to traversing along a line joining, here line by line I mean a curve, joining two points which are determined by, determined by initial positions in the original terrain, in original terrain. So minimization of the cost corresponds to traversing along a curve joining two points which are in turn determined by the initial positions in the original terrain, such that the length of the curve is minimum. So that is what it boils down to. It basically takes a path in this surface which has the minimum length and joins the 2 points. Okay. So let us just stop here for a moment and consider. So now consider a particle or some mechanical system. So consider a particle or some mechanical system given some initial conditions and some kind of constraints, given some, I would say, boundary conditions and some set of constraints. Now given this, how do we predict the trajectory of the particle? The trajectory of the particle. So this is the main question that we will be answering in mechanics. How do we predict the trajectory of the particle? Now we know already that this trajectory is determined by the equations of motion. So determined by equations of motion. But how do we get these equations of motion? That is the question we are trying to answer. So what is the basis, or what makes the system or particle follow these equations of motion? And that is what we are going to try to answer using the principle of least action. Okay, so what principle of least action what does principle of least action say? So what it says is that every mechanical system is characterized by a definite function, which I am going to denote as L, which depends on the generalized coordinates, the generalized velocity and time, and the motion of the system is such that certain conditions are satisfied. So what are these conditions? We are going to see this soon. So let's consider the system. So I'm going to define this as the time axis and this as the x-axis, where this x denotes all the set of generalized coordinates and the generalized velocities. Now let's say that the system is at time t1 is at some initial state defined by x1, and at some time t2 goes to some final state defined by x2. Now the system can go from this initial to final state through many different paths, but we know that only one of these paths is going to be the correct path, or the path which follows the equations of motion. And the claim is that the system moves between these two positions or these two states in such a way that the integral, so the claim is that system moves between these positions in such a way that the integral given by t1 to t2 L q dot t dt is minimized. So this is the claim. And if you have seen my video on Euler-Lagrange equation, this is minimized. So this is minimized when this particular set of equation called the Euler-Lagrange equations are satisfied. So here this S denotes the number of degrees of freedom. Okay. So from the previous video on Euler-Lagrange equation, this particular integral is minimized when these sets of conditions are satisfied. Okay, so this is the claim. Now how do we better understand this? And that was the whole point. So let's understand this using our analogy, which was the ball rolling down a terrain. So this was that ball down the terrain. So how do we connect this to the analogy? As we make the connection, this argument will become more clear. So the connection or the analogy is as follows. So in our case of ball rolling down the terrain, we are going to make the following analogies. Okay. Now the terrain or the hill is analogous to some function describing the system or the setup of our given mechanical problem and the constraints. So what do I mean by this? So if you consider, let's say, a spring mass system which is constrained to move only along the x axis or x direction, then this particular setup is going to, in our analogy, is going to correspond to some particular terrain in the x dot and time coordinates. Okay, so a better representation would be, let's say we have time here and we have the x coordinate, which basically represents both x and x dot, and this is some function f, this function, which describes, so this describes some terrain on which we can define the various different paths which the particular particle or the system is going to take. So these paths are the same as these paths. Okay. So the first analogy is that our terrain or hill is analogous to some function describing the system and the constraints, which basically corresponds to a surface or a terrain defined in this particular space. So we have gone from our x, y, z space to the generalized coordinate, generalized velocity and time space. So our new terrain or our analogous terrain is actually defined in a universe or in a world where these form the three axes. And every point in the terrain corresponds to a particular time instant with the particle having a generalized position given by this particular q vector and the generalized velocity given by q dot vector. Okay. Then the trajectory of the ball is analogous to the path of the particle in the xt space, which is this space. So that is our second analogy. I hope you understand what I mean by this. So basically, the trajectory of the ball here. So these different trajectories are analogous to these different trajectories. Okay. And the terrain is analogous to some function which describes the system in the q dot and t space. Then we also had defined the weight function, which depends on some quantities k1, k2 defined earlier, and this is analogous to the function L, which depends on q dot and t, and this function is called the Lagrangian. So you see where I'm going here. So our weight function in the previous scenario is analogous to this Lagrangian function. So this Lagrangian function gives some sense of weight for each of these paths, which is basically a collection of traversals or sum of traversals. And this integral is basically some weighted sum of these traversals. And that is the analogy that we are making. So our weight function has now become the Lagrangian. Okay, and these k1, k2 dot 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 have now become q dot and t. So obviously analogies are not exact, but they are something which helps us to understand the concept better, and that is what I'm doing here. So I'm not making precise mathematical statements here. That is why I'm not writing equal to here, but this represents analogy. Okay, and our dl, that is our traversal, was basically defined by an infinitesimal length element. In our case, when it comes to the principle of least action, this becomes dt, that is an infinitesimal change in the time instance. Okay, and the cost for a path in our previous case has now become this integral s, denoted by s, which I had already written down, q dot t dt, and this s is called as the action, and that is where the name comes, principle of least action. So our cost integral or cost for a path in our previous case is analogous to the integral which we call as the action. And the condition for cost minimization which was basically choosing direction along gradient of the potential function, is analogous to the Euler-Lagrange equations, which are nothing but these. So according to the analogy, whenever this particular condition is satisfied, the corresponding cost becomes minimum. So that is what the analogy is trying to say. Okay. So to summarize what we have done in this video is that we try to understand something known as the principle of least action, and what this principle of least action says is that every mechanical system is characterized by some function called the Lagrangian, and given some initial boundary conditions, the path or the trajectory which the mechanical system takes is, or it corresponds to this particular integral taking the least value. And for this particular integral to take the least value, these sets of conditions called the Euler-Lagrange equations must be satisfied. And we understood this principle of least action through an analogy of a ball rolling down a hill with infinitesimally small speed. And according to this analogy, what we are trying to see is that our terrain or our hill is analogous to some function which describes the system and the constraints, and we are moving from the xyz coordinate to q dot and t coordinate, and our trajectory of the ball is analogous to the path of the particle in the xt plane, and our weight function is analogous to the Lagrangian, and our traversals in length is analogous to our traversals in time instances, and the cost for a path is analogous to the action integral, and finally the condition for cost minimization is analogous to the Euler-Lagrange equations. And I do know that this video was a little bit messy and lots to take in, but since this is something which is a bit abstract and we do not come across these kinds of equations in our day-to-day life, I thought that giving this or explaining this principle using this particular analogy of a ball rolling down a hill would make it easier to understand this principle of least action. And that's it for this video. Thank you for watching.